Hi there. Okay, I want to look at just a couple examples from section 4.4, and this deals with the logistic model. It's a variation on exponential growth. We know that our exponential growth model is unbounded, so the model looks something like this. And is really only realistic in the short term, except for things like money. But if you have a closed system like a lake, you couldn't have the population of fish grow without bound. There's going to be some equilibrium population or carrying capacity. So what the logistic model does is it actually changes shape. So early on, it looks kind of exponential in form, and then something happens. And if you look here, we're concave up here, and over here we're concave down. So what happens is we have this point here, which we know is a point of inflection, where concavity is changing. And what that does is it allows our population in the long run to approach what we call a carrying capacity. You could also refer to it as a saturation level or an equilibrium population, depending on the context of a problem. So this point of inflection here in the economics world is called a point of diminishing returns. In the bio world, just a point of diminishing growth. And the idea in an investment situation is you're still gaining a return on your investment, but it's starting to happen at a slower rate. It's becoming less steep if you looked at tangent lines here. Whereas early on, you're getting steeper as you approach this inflection point. Okay. And so I'm using a slightly simplified version of the formula you might find in the book. They make it a little more complicated than it needs to be, so this will suit our purposes just fine. One of the nice properties about the logistic model is that the point of inflection always occurs at half of the carrying capacity. Usually, at least in the past, in order to find out where points of inflection were, you'd have to take a second derivative and set it equal to 0. And looking at our formula, we probably don't even want to take the first derivative, although we will. But certainly a second derivative would be a little bit of a pain. So what we can do instead is we can actually set the model itself equal to half the carrying capacity and solve for time that way, and that'll give us this value. There's a formula here as well, but I'd rather work with the algebra that we need to learn anyway. So this is our carrying capacity. It's sort of like exponential growth in the short term, and then changes inflection. This is the curve that you're seeing all over the news. Okay, you're not quite, maybe not seeing this curve as much, but its derivative actually looks kind of like this. This value here is where that point of inflection is. So this is actually like the derivative of the logistic model. And they keep talking about flattening this curve out, right? What they're trying to do is move that point of inflection over so that you get a much more gradual rate of spread of this coronavirus. So the flattening of the curve thing that you're seeing on the internet and on news is really the derivative of this model. So we're going to play around with this model a little bit and see that it's a much more realistic application of exponential functions. So this is not considered an exponential function itself, but it has an exponential term in it. So let's just look at a couple applications. This first one here seems like a reasonable application that if we're looking at the height of a particular plant, certainly a plant can't grow to an infinite height. There's going to be some saturation height or equilibrium height for pretty much all plants of a particular species. So we're going to look at this a little bit. So this gives the height in inches after t days. Okay, so the initial height for our experiment here, this is when t is 0. So we're just looking for h of 0 here, which would be 21 over 1 plus 25 e to the 0. And e to the 0 is 1, so we have 21 over 1 plus 25, or 21/26. For an application problem, it's probably worthwhile just to go ahead and go to decimal. So this is about 0.81 inches. So pretty short. This would be like a seedling that is just sprouted. And so we're considering time 0 maybe as the time at which we take it from incubation to actually planting it in a planter or something like that. Or it's just the first recorded bit of information. So that's our initial. How do we find the expected height for a full-grown plant? Okay, this is actually a long-term height or a limit. So if we look at the limit as t goes to infinity of h of t, it seems like a complicated limit at first. What I'm going to do is I'm going to rewrite this denominator without the negative exponent. So we would have 21 over 1 plus 25 over e to the positive 0.3t. And what this does for me is it makes it a little easier to see what's going to happen here. This term, as t grows infinitely large, will go to 0. And that'll just leave me with 21 over 1, or 21 inches. So this would be the expected height of the average plant. Some certainly would be a little above, some a little below, but this is what basically would be the cap on height, at least the expected cap. Okay, so let's scroll down a little bit here. Now I want to know how fast the plant is growing after 2 weeks. So we know how fast is asking for a derivative. Okay, so we're going to have to find h prime. Also, 2 weeks, you have to be careful here. The function was defined in days, so 2 weeks would be where t is 14. So what we want here is h prime of 14. Okay, the first thing I'm going to do is I'm going to rewrite h, and I'm going to bring that whole exponent, or the whole denominator, up to the top using negative exponents. So I'm going to write this as 21 times 1, excuse me, plus 25 e to the negative 0.3t to the negative 1. And then I'm going to use the chain rule. So our derivative, h prime, will be negative 21. Let me fix that. This will be negative 21 times 1 plus 25 e to the negative 0.3t to the negative 2. But then we also have to multiply by the derivative of the inside. 1 plus 25 e to the negative 0.3t. So just the usual application of the chain rule. So we have this part out here that's already done. Negative 21 times 1 plus 25 e to the negative 0.3t to the negative 2. The derivative of 1 is 0, and then we have 25 e to the negative 0.3t, but we also have to multiply by the derivative of that exponent, which is negative 0.3. So there's our derivative. Now all I need to do is use my calculator, and you should double check that you can get the same answer. But when I plug 14 in for t in both of these spots here, be real careful with parentheses and everything, what you should end up with is approximately 1.249. And what are the units here? Remember, this is a derivative, so it's a rate of change. It should be something per something, rise over run. So in this case, it will be inches per day. And do note that because it's slope and it's positive, this does say that height is increasing. So that's the rate of growth at the 14-day mark. Okay, that's all for this page. On to page 17.